1. This is chapter 4. And in chapter 4, what you're going to look at is some applications of the derivative. And at the end of chapter 4, we'll start to undo the derivative when you look at the integral, which is what we've been talking about as we're going. But before we leave that, we're going to look at one of the main applications of the derivative is to help us maximize and minimize functions, maximum profit, minimum cost. You can imagine maximizing output, maximizing volume, maximizing surface area. Also just curve sketching. You know how to find the maximum of a parabola because you know, or minimum of a parabola, that's called an extrema, because it occurs at the vertex. And you know the equation for the vertex. Vertex is negative b over 2a. You know that's the x-coordinate, and you can find the y-coordinate. You learned that in college algebra. But any more complicated polynomial, and you don't know where it has maybe a local max or a local min, you can graph it on your calculator, and you can do second calc max. But to actually prove where that max exists requires calculus, because what you're going to do is you're going to say, oh, you know what? When I have a max, what's true about my tangent line? The slope of the tangent line is 0, and that's true for a min too. So if you take the derivative of a function and you find where its tangent line is equal to 0, then you have the only possible location that you could have a max or a min.
So you just take the derivative and set it equals 0?
Mm-hmm. Well, and then once you know that's where it's equal to 0, you actually have to test to make sure there is a change, because the slopes are going to need to change. See how it's going? The slopes are increasing, and then it's 0, and then they're decreasing.
Okay.
If, like, say, I can't really do it with my arm, but if I was one of those bendable, like a cubic function that, it's actually 0 for an instant, but it's always increasing, so it doesn't change. So you do have to test, but the first thing you do is take the derivative and set it equal to 0, and then you determine whether it has a max or a min there. Okay? All right, so that's what we're going to look at today. The first lesson is kind of just a warm-up for that, and what happens in this lesson is we're going to define absolute maxes and mins, and we're going to actually look at them on closed intervals instead of over the entire number line. That cubic function that I drew like this, the absolute max and min is positive infinity and negative infinity, right? But it has what we call local max and mins, which are those little bumps. But if we had restricted the domain, like say it was here, we restricted the domain and it went up, that might have been a max, an absolute maximum, if you had stopped it. Okay. All right, so here we go in section 4.1. So we're going to define absolute and local extrema. So this will be a formal definition that you can enjoy. So let f be a function with domain D then f has an absolute, I spelled that wrong, sorry, max on D at a point C if for any time you put an x that's around C and anytime you evaluate the y value, you're always less than f at C for all the x's in the domain, right? So for all the x's in the domain, you plug them into the function and you get a y value that's less than when you plug C in. That makes sense, right? It's just kind of a hard way to say it, but we like to practice using math language in this level of course. Okay? And an absolute min value on D at C if, what do you think would be true?
If functions of x are greater than other functions of C.
And this would be the function of C.
Yep.
Yeah. And for all x in D. So as long as they're all the x's are greater than all the f of x's, all the y values for all the different x's are bigger than the y value when you put the C, then you have an absolute min. And it says Okay, so that's those are absolute. So that's for all x's in the domain. Now we want to define now in local extrema. So this was an absolute min versus an absolute max. A function f has a local max at an interior point C of its domain if f at x is less than f of c or equal to for all x in an open interval containing C. Okay, so what you're imagining is if you have a, can you put a little interval around it so that it makes it the highest value? So like for example, if you have a function like this that goes like this, we would say that this is a local max here at C. And the reason is because we can find an open interval like maybe from here to here, so on the x-axis, from there to there, where that C is the highest value. That's what it means to be local. It's not an absolute though, because it's not from negative infinity to positive infinity. You know what I mean? Because if you made it bigger, you could like if your interval were like from here to here on the x, then this number would actually, whatever you have up here would be higher than that one. So you just have to find one area where it's the maximum. Okay. So that's local. And then you can imagine, I'm not going to write the definition of a local min, but it's similar. Okay, now the extreme value theorem tells us if a function f is continuous on a closed interval, A, B, then f attains both an absolute max which we'll call big M, and an absolute minimum.
Even if it's a straight line?
Well, then that's kind of the degenerate case, but it is what it is. You know, it's always the same.
Yeah.
But yeah, the max is the min is the value. But that's a good question. This is kind of it seems like sort of an obvious question, but an obvious theorem, but it's really comes up a lot. If you have a continuous function, because you don't always know you may not always know what to do with it, but if you have a continuous function on some interval, say from A to B, on that interval, this is a closed interval, it will take on an absolute min and an absolute max. And it could be that it's within the interval, it could be at the endpoints, or it has to be closed. So it could be at the endpoints, or it could be where the derivative equals 0. But if it's continuous, what you want to do, and that's all we're going to do in this homework, is you're going to take the derivative, set it equal to 0, and find the horizontal asymptotes, or where it's undefined, because you could have a cusp there. And then you're also going to check your endpoints. And then you're going to plug the places that the function is, the derivative is 0, you're going to find the y value. Where the endpoints are, you find the y value. And if the derivative is undefined, you find the y value at those places. And then you just pick the largest one and call it the max, and the smallest one you call it the min. Does that make sense? So, because somebody has to be the winner if you're in a closed interval and you have a continuous function, right? Now, it could be that they're all winners if you have a boring function. That's just the horizontal line. You're all winners.
And if there are two, would you just list both of them?
Yes, yeah, if they're matching, or like if they're, yeah, sure. Okay, so let's look at number 3 here. It says determine from the graph whether the function has any absolute extreme values on a, b, and then explain how your answer is consistent with the extreme value theorem. Okay, now, oops, that's from last time. The extreme value theorem requires that you have the function. What were the conditions? It required that the function be continuous. That's all it needs, continuous on the closed interval. So is this function continuous?
Yes.
Okay, so we have the hypothesis satisfied. So this is continuous on the interval from a to b. So all we have to do is say where the absolute max is and where the absolute min is. So does anyone want to give me a sense of where the absolute max is? Mm-hmm. Max. And so we can use the language. It's going to be a absolute max of h of b, because the function is called h of x. So h of b at x equals b. And then where does it look like we have an absolute min?
H is C2 at
Mm-hmm. Absolute min at h of c, this is the value that it will be, which is h of c2, whatever that is. This y value is h of c2. And this y value over here is h of b at x equals c2. And what you notice, do you guys notice that right here you have what? What's true about h prime of x right here?
0.
It's 0. And so it's consistent. It is where it's 0 and it's also where it has a min. But right here, what do you notice? Well, h prime is 0 right there, right? But in that case, it's actually h prime at c1. But that's not the absolute max on the closed interval. So we really have just what we call a local max here.
And that would be H prime of C2 right?
Yeah. This one turned out to be an absolute min because we had a closed interval. Yeah.
Well, it's something like the b point, the derivative wouldn't be 0 at that point.
That's right. But because you have a closed interval, the question was when it's the b, you don't know about the b. You don't have a derivative equal to 0 there. But if you have a closed interval, you always have to check your endpoints. So you actually, if you were doing this, if you knew the function, you would actually find the y value at a, the y value at C1, the y value at C2, and the y value at B. And then you would pick the one that was highest, it would be the max, and you pick the one that's the lowest, and it would be the min. Do you see what I'm saying? But right, when we have functions that are continuous over an entire interval from negative infinity to positive infinity, well then that's when we'll probably most of the time, or a lot of times only get like a local max. We may not get an absolute max, because cubic functions and such could go off to positive infinity and negative infinity. It just kind of depends on the nature of the function. All right, what would we say about this function? Yeah, it's not continuous, so we can't make the argument for the extreme value theorem. We just no luck there. Okay. So on the closed interval from A to B. Now we could, if they'd asked us to say, okay, well, what about from A to C? Because it does look like it's closed from A to C. If you looked at A to C, then that would be, it had a min at A and a max at C. But it didn't do that.
And it would not be closed from C to B, correct?
Right, from C, because we have an open circle at C, so no. Okay. All right, so now we've got a theorem. It's called the first derivative theorem. If f has a local max or min value at an interior point of C, say at an interior point, and we'll call it C, of its domain. When I mean F's domain. And we know that f prime of C is defined if that is true, then it must be true that f prime of C is equal to 0. Okay? So, the only places an extreme value can occur are, we have 3 places. 1, interior points where f prime of c equals 0. We could have an interior point where f prime of c is undefined. And finally, the endpoints of the domain. So what you have now, if you didn't have your graphing calculator, is you know at least where the only places you have to look to determine if a function has a max or min. You don't need to be looking all over the place. You need to look where the derivative is equal to 0 or undefined, and you need to look at the endpoints. That's how you can figure out where a max or min value is for a particular function. So that's pretty exciting. Okay? And it turns out a critical point is that place where you need to look. So it is either an interior point of the domain where the derivative is either 0 or undefined. So a critical point is an interior point. Are y'all okay with interior? Because that means it's not one of the endpoints, because those are considered separately. So an interior point of the domain of a function f where f prime is 0 or undefined is a critical point of f. Okay? So you hear me a lot say, let's find the critical points. So all you're going to be doing is figuring out where the derivative is equal to 0 or undefined, which is why you spent all those years in college algebra or in algebra trying to figure out where a function equals 0. That's all for this big moment in time. Okay. What is the process for finding an absolute value of an extreme of a continuous function on AB? Okay, so this is, I'm just going to write it down, what I already sort of described. The first thing you'll do is find the critical points. Notice that the interval is closed. So you're going to find the critical points. Which is, means to determine where f prime of c equals 0 or is undefined. And then the second thing you'll do is evaluate f at all points, at all the critical points, and the endpoints. So you're going to figure out where the derivative equals 0, and then you're going to plug that into the original equation and get a y value. And you're going to plug the endpoints into the original equation and get the y value. And then you're just going to compare them. So you take the largest and smallest of these values.
And there wouldn't be any undefined f prime of c in here, would there? Because it's a continuous function.
No, there can be. Remember, like the absolute value function? And those little cusp ones Those can be, yeah. The continuity, you can still have continuity, but still have a derivative that's undefined. It's called a vertical tangent that occurs there. Smallest, take the largest, or a corner. Smallest of these values. Remember, you have to kind of expand your mind on functions. You can define functions piecewise that are still continuous, but they're really strange, like they're bendy and then curvy, you know, and then they have corners, which is where you're going to have trouble. Or just interesting. All right. What we're going to do is we're going to find the absolute max and min value for each function on the given interval, then graph the function. And we're going to identify the points on the graph where the absolute extrema occur and include their coordinates. Okay. This one is kind of lame, but anyway, I don't know. This is what kind of function is this? It's a linear function, and so we would expect it to be doing what between -2 and 3?
Going up.
Yeah, increasing because it has a positive slope. But just for fun, we'll go ahead and do the problem. F prime of x is what? It's equal to 2/3. So it's never 0 or undefined, right? So that kind of, we don't get to do anything with that one, all right? So we only need to check what? Yeah.
And were the endpoints critical points as well, or were they?
No, they're just going to be endpoints. Only need to check the endpoints. So we go ahead and evaluate f at -2. We'll get 2/3 times -2 minus 5, which is -4/3 minus 5. This is like 15/3, so that's going to be so -19/3. And then we can plug in f at 3. We get 2/3 times 3 minus 5, which is 2 minus 5, which is -3, right? 19/3 is like -6 1/3, right? So here, and then what did we put in 3? So it looks something like this. Obviously, it's just a line. And so clearly, this is the min, right? And this is the max. So this is our minimum value. We have a min of -19/3 at x equals -2. And we have a max of -3 at x equals 3. Okay? Maybe number 8 will be more exciting. Okay, so f prime of x is what?
-1 over x cubed.
Almost. So this is x to the -2 power. So what's the derivative of that?
-2 over x.
Okay, so I'll write it. So f of x is equal to x to the -2 power. So f prime of x is going to be -2 over x cubed, right? -2 over x to -3. When is that equal to 0? Good. When is a fraction equal to 0? Never. The fraction can only equal 0 if the numerator is 0. But this numerator is 2, and so it can't be 0. So this is never 0 because the numerator is constant. But, so that's for f prime. But f prime of x is undefined at x equals 0, right? Because we have it's not, okay. But, what can you tell me?
That doesn't matter because
Good. 0 is not in our interval from -2 to -1. So we can just check the endpoints again. Brooks, this isn't very exciting. I know. Don't worry, it gets worse. So f at negative 2, this is going to be 1 over negative 2 squared, which is going to be 1/4. And f at negative 1, which is going to be 1 over negative 1 squared, which is positive 1. Okay? And so what do we have at negative 2? Yes, your choices were min or max. You picked the higher number, and it's the maximum. You picked the lower number, and it's the minimum. Are y'all lost? So this one, at negative 1, you get a y value of 1, and 1 is bigger than 1/4. And so this one is the max, and this one's the min. The graph of 1 over x squared is your friend. It looks like this. It's got an asymptote here and here. You know, I got y equals 0 asymptote and x equals 0 asymptote. But from negative 2 to negative 1, it's increasing. So it's just, that one's the min and that one's the max. It's not very exciting. It doesn't bend or anything. Okay. You ready for a really exciting one? All right. How about this one? Oh, yeah. Cosecant. Gotta love it. All right. We need to figure out, here's our interval. What do we need to do? Well, we need to figure out what g prime of x equals 0. So we need to figure out what g prime of x is. And does anybody remember the derivative of the cosecant? Negative cosecant x cotangent x? Yes. All right. And cosecant is 1 over sine. So this is negative 1 over sine of x times cotangent is cosine over sine. Right? So this equals 0 when negative cosine x equals 0, right? Because a fraction equals 0 when the numerator equals 0. And g prime of x will be undefined when the denominator, which is sine squared x, equals 0. Does that make sense? Okay. So on the interval from pi over 3 to 2 pi over 3, think about your unit circle. Here's pi over 3. And here's 2 pi over 3. When does the cosine equal 0 on that interval? Yeah, which is at pi over 2. So this is true when x equals pi over 2. And when does the sine equal 0 on that interval? So this is never, not in the interval. The sine equals 0 like at 0 and 180, you know, or so 0 and pi. But our interval is only from pi over 3 to 2 pi over 3, so the sine is never 0 there. That's the y value.
Negative cosine x would be 0.
It doesn't really matter because cosine x equals 0 and negative cosine x equals 0. So just you can divide through by negative 1 and just figure out where cosine x equals 0. Okay, everybody happy? So we got one critical point. We have the critical point pi over 2, and then of course we have our endpoints that we have to test. All right, so now what you do is you take your critical points and your endpoints, you plug them into the original function, you figure out what they are, the largest one you call your max, the smallest one you call your min. All right, so we'll check, and it's nice to kind of put them in order. So we'll do f at pi over 3, or sorry, g at pi over 3 is the cosecant of pi over 3. Remember, cosecant is 1 over the sine. 1 over the sine of pi over 3. And you might remember that's the sine of pi over 3 square root of 3 over 2. So if you reciprocate that, that's going to be 2 over the square root of 3. Or if you look at that as a decimal, it's about 1.1. Now, g of pi over 2 is equal to the cosecant of pi over 2, which is 1 over the sine of pi over 2. Sine of pi over 2 is 1, though, so that's 1. And g of 2 pi over 3 is equal to the cosecant of 2 pi over 3, which is 1 over the sine of 2 pi over 3, which is in the second quadrant. It's still positive, so it's 2 over the square root of 3, which is still 1.1. So these are, this is a place where you have two maxes. This is 1.15, I guess. So this is an absolute max at pi over 3, and an absolute max at 2 pi over 3, and an absolute min at pi over 2. And so you could graph this and see, you remember it makes that little bowl, the cosecant graph? So that you must be seeing that at pi over 2. Okay, let's look at number 10. H of x equals e to the negative x squared. H prime of x then is going to equal what?
Negative x squared, negative 2x.
E to the negative x squared times negative 2x. So this is negative 2x e to the negative x squared. So when will that derivative equal 0? Good. This equals 0 when x equals 0. Obviously, if you put 0 in, it'll zero it out. You don't have to worry about e to the negative x squared is never going to be 0. There's no way to raise a number to a power and get it to be 0. So the only thing that you have to worry about is what makes 2x 0, which is 0. X equals 0. Okay. So now we're going to check the endpoints, h prime at 2, the interior point where the derivative was 0 or undefined, and then h at 1. And nowhere is this function undefined. The derivative is continuous. Okay, so h at negative 2, you plug it in here, it's going to be e to the opposite of negative 2 squared, which is going to be e to the negative 4. H at 0 is going to be e to the opposite of 0 squared, which is going to be e to the 0. And h at 1 is going to be e to the opposite of 1 squared, which is just e to the negative 1. All right. Well, go ahead. This is 1. This is 1 over e to the 4th. And this is 1 over e. So which one's the biggest and which one's the smallest? 1 is the biggest. So this is an absolute max. And which one's the smallest? Yeah, and this is absolute min. Because if you have a larger denominator, it's going to be a smaller number altogether. Okay. For problems 11 and 12, find the extreme values of the function and where they occur. Remember to consider the domain of the original function. Okay. So what is the domain of this function? Well, it must be true that 1 minus x squared is greater than 0. Do y'all agree with that? Because you can't take the square root of a negative number and you can't have 0 in your denominator. This is your friend the parabola shifted up 1 and then reflected. So it's from negative 1 to 1 is the only place that this is going to be defined. The rest of it is not going to work. Okay? So the domain is negative 1 to 1. And so on this one, we're going to have to go ahead and we don't have a closed interval. So we're going to have to kind of make an argument to whether we have a max or a min looking at where our derivative is either undefined or 0. But if you look at it, let's go ahead and take our derivative. So you might want to think of this f of x as, when it's just a constant up front, I often just don't like to use the quotient rule. I just like to use the chain rule. And so I would write this as 1 minus x squared to the negative 1/2. It's just going to be easier to take the derivative. So f prime of x is going to be negative 1/2. 1 minus x squared to the negative 1/2 minus 1, which is negative 3/2, times the derivative of that, which is negative 2x. And so those 2's cancel and negatives cancel. So it's x over 1 minus x squared to the 3/2. Now, you do see that at 0, you're going to have, when x is 1 or negative 1, you have trouble with this, but that's not in the domain, so you're good there. We have to figure out when does this equal 0? When does it equal 0? Yeah. All right, and then it's undefined at x equals 1 plus or minus 1, but those are not in the domain. So we only have one number to look at, right? So how are we going to figure out whether it's a max or a min? Well, what we can do is we can compare numbers to the left and right of the number that we have, and if it's lower than those two, we can argue that it's going to be the lowest, or if it's the higher than those two on either side, we can argue that it's going to be the highest. So since we know it's continuous. So let's look at, consider f at 0.5, f at 0, and f at negative 0.5. All right, if you do f at 0.5, that's going to be 1 minus 1/2 squared, which is 1/4. So this will be 3/4. And so, and you take the square root, so it's the square root of 3 over 2. So this is 2 over the square root of 3 for both of these. Which is about, we learned that a second ago, 1.15. When you plug 0 in here, what do you get in the original function? If you plug 0 in, it's going to be 1 over 1 minus 0, which is just 1 over the square root of 1, or 1. Okay? So what do y'all want to say you have at 0?
X.
I know 0 is a critical point, so I know that's where my derivative equals 0, okay, at 0. And then I picked a number to the left and the right of it, and I got those numbers to be actually greater than the y value at 0. So I would actually say that it's going to be a, does it feel better that it would be a min? Because it's the lowest one. So this is going to be a min. We argue that x equals 0 is a min.
Did you draw your graph there upside down?
Pardon?
Did you draw your graph upside down?
Good question. All I did here was look at the graph of this denominator, because I was trying to, not even of the denominator, of the stuff under the radical, because I was trying to describe the domain. That's why I drew that. That's not the graph of this function. Are you okay? Okay. Yeah, I threw you off, didn't I? Okay, let's look at number 12. What is the domain of the inverse cosine? You guys remember? Do you remember what the range of the cosine is? If you do, then you can tell me what the domain of the inverse cosine is.
0, pi.
That's the domain. What is the, that's the range. What is the domain? What's the range of the cosine? What kind of y values do you get for your cosine? Or
-1.
okay, so from -1 to +1. And so that is going to be the domain of the inverse. Because remember, the inverse functions switch your x and y. So the domain of this function is from -1 to 1. So now we have endpoints that we're going to check, and then we're also going to see where the derivative equals 0. All right, you have to look on your sheet unless you remember it. The derivative with respect to x of inverse cosine of u is -u prime over the square root of 1 minus u squared. Y'all remember that? Or you can look on your sheet. Well, here, what's our u?
X.
Yeah, x squared. And so u prime is equal to 2x. So the derivative with respect to x of the inverse cosine of x squared is going to be equal to u prime, negative u prime, so negative 2x over the square root of 1 minus x squared, which is negative 2x over the square root of 1 minus x to the 4th. All right, and so when do we have critical points? What are our critical points? So this is y prime.
X equals 0.
Uh-huh. When x equals 0, because that'll make the numerator 0, and when x equals plus or minus 1, because that's going to make this messed up. But these are already our endpoints. Those are already endpoints of the domain. Okay, and so we do when x equals -1, when x equals 0, and when x equals 1, we find f of x. So we're going to do the inverse cosine of -1 quantity squared is the inverse cosine of 1. So when is the cosine 1? The inverse cosine. When is the inverse cosine 1? For what angle is the cosine ratio 1?
0 or pi.
Yeah, but it's only defined, yeah, so for 0. Okay, and then what is the inverse cosine of 0? For what angle is the cosine 0? When does that occur? Do y'all remember? Pardon? Good, 90 degrees, which is pi over 2. And then this one, we already know the answer because it's the same. And this is 0. All right, and so why did we do this? Because we're looking for local max and mins. So which one is our max? Or not local, absolute, actually. Which one's our absolute max? Yeah, absolute max, because that's the biggest number. And we have 2 absolute mins at -1 and 1. Got a big space here. Okay, so now it says for problems 13 and 14, find the derivative at each critical point and determine the local extremes. Okay, so if you look at the domain of this one, it is from -infinity to +infinity, because you can take the cube root of anything and you can take, x plus 2, that's just going to be as a product of 2 functions that have domains from -infinity to +infinity, so you're good to go. Okay, so we need to take the derivative and set it equal to 0 and see what we have going on there. So we will use the product rule. This will be my u and this will be my v. U is equal to x to the 2/3, so u prime is equal to 2/3 x to the 2/3 minus 1, which is -1/3. V is equal to x plus 2, so v prime is equal to just 1. Okay, and so our product rule is u times v prime plus v times u prime. So y prime is equal to u times v prime plus v times u prime, which is going to be x to the 2/3 times 1 plus x plus 2 times 2/3 x to the -1/3, which you can write this as x to the 2/3 plus, right, this will be 2 times x plus 2 over 3x to the 1/3. You're actually, this is a little technique that you do a lot, but you're going to want to get a common denominator, and when you do that, it makes the numerator really pretty. The common denominator will be that 3x to the 1/3, and you're going to multiply that by top and bottom. And this is 3 times x to the 1/3 times x to the 2/3. What happens there?
You get 3x.
Good, you get 3x. Because remember, when the base is saying you add the exponent, so 1/3 plus 2/3 is 3/3. And then here you get 2x plus 4. If I distribute that out. So this fraction cleans up to be 5x plus 4 over 3x to the 1/3. Okay? And remember, you want to see when this is equal to 0 and when it's undefined. So when is it equal to 0? Okay, so equals 0 at x equals -4/5, right? Because you just take the numerator and set it equals 0. And it's undefined where? At x equals 0. Does that make sense? All right, so now we have 2 points that we won't be able to say whether they're absolute max or mins, but since I have 2, I'll be able to compare them and say which one's the max and which one's the min between the 2. And we'll say they're local max or mins. Okay, so how is it that I figure that out? I take the value I get for where the derivative is equal to 0 or undefined, and I plug it where?
The original function.
Into the original. If you plug it back into the derivative, you're going to get either 0 or undefined. So you've got to remember to plug it back into the original function. Do you know what I'm saying? When you're working through these. Okay, so let's call this f of x. And so if I do f at -4/5, that's going to be -4/5 to the 2/3 power times -4/5 plus 2. And if you type that into your calculator, you should get about 1.034. And if you do f at 0, clearly you're just going to get 0. And so this one will be the local max, and this will be the local min. Since my interval's not closed, I can't say whether it's absolute or not. Okay? So this one's kind of an interesting problem. It's a piecewise defined function when we're looking at 1 and or what happens at 1. Okay, so let's look at this function first. If you put 1 in here, you're going to get -1 minus 2, which is -3, plus 4, which is 1. And if you put 1 in here, you get -1 minus 4, and then the plus 6 is also 1. So this function has a corner at 1. But it is continuous. So it's going to change shape sharply, but because you get the same value when you put 1 in coming from the left or the right, your limit exists there. It's just that your derivative doesn't. You're going to have a corner. So your critical points are going to be where the derivative is undefined at x equals 1, and also where each of these equals 0. So where -2x, where each of these derivatives, -2x minus 2 equals 0, and where -2x plus 6 equals 0. And so this is going to be x equals -1, and then this one's going to be x equals -3, positive 3. Okay? Okay, and so what you do is you just test your values. You're going to want to test when x equals -1, when x equals 1, and when x equals 3. And so this is kind of fun because you get to decide which one you want to put it in. Where are you going to put the -1? In which of these equations will you put it in? In the first equation, yeah. So you'll do the opposite of -1 squared minus 2 times -1 plus 4. So this is -1 plus 2 plus 4, which is 5. If you put 1 in, you're also going to put 1 into that first equation because it was less than or equal to. So it's the opposite of 1 squared minus 2 times 1 plus 4, which is -1 minus 2 plus 4, which is 1. And you'll plug 3 into the second equation. So 3 squared plus 6 times 3 minus 4. It's -9 plus 18 minus 4. So that's 5. And so we're going to have a local max at -1, or actually, yeah, local max at -1 and, and at 3. And we have a local min at 1. Okay. All right, and so here's an application problem. It says supertankers offload oil at a docking facility 4 miles offshore. The nearest refinery is 9 miles east of the shore point nearest the docking facility. A pipeline must be constructed connecting the docking facility with the refinery. The pipeline costs $300,000 per mile if it's constructed underwater and $200,000 per mile over land. So we want to locate a point to minimize the cost of construction. All right. So you can kind of imagine probably an expensive way to do it, maybe, would be to go straight here from the docking facility, the very shortest distance possible to the shoreline. And the reason you might do that is because it's most expensive to construct it underwater. So you want to do the shortest possible amount. Does that make sense? Yeah. And then you would go straight to the refinery, right? But it's possible that there may be a location where you could kind of go here and then to here, and it would minimize the cost. It would be less than going straight, because this distance, if you went boom, boom, that's going to be a lot of distance, right? Whereas if you went from here to here, it's going to be less distance that you have to cover. Now, the other thing is to just take it straight to the refinery from the docking facility, right? That would be the most, straight from the refinery, that would be very expensive perhaps, because that would do the whole thing underwater. Does that make sense? So this is kind of your problem. Now, what I want to do first to kind of make our numbers smaller is I want to talk about them in terms of millions of dollars. So my cost function, I'm going to write in millions.
Would it be better to write in millions of dollars?
I don't know. According to my notes, it's better to write it in millions. Yeah, but yeah, I know this. I'm doing it this way just to mess with your mind.
Oh, okay.
All right. So what is 300,000 in millions? Yeah. Did you hear him talk about 0.3 million, 0.5 million?
Yeah.
So I don't know why I'm doing it. I think just to be consistent with the homework. All right, and then 200,000 is going to be 0.2 million, right? And also because it's per mile, it's going to get high pretty fast. Okay, all right. So you can imagine, like, if you just went straight here and then straight here, it would be what? 1.2 million underwater, and then it would be 1.8 million on shore. Are y'all feeling that? Because it's 4 miles and it's 300,000 per mile, right? Yeah. So this would be 1.2 million, and then this would be 1.8 million, which would be 3.6 million if you just went. Is that right? Oh, 3.0 million. $3 million. God, if you just went straight there. Now, what about if you did it this way? Well, you'd have to figure out what that is, which would be the square root of 81 and 16 is square root of 87 times, does somebody want to do that, 0.3?
Be 97.
97? Square root of 97 times 0.3. You got a calculator, Amy? Or?
It's 2.95 million.
Okay, so that that seems at least smarter than doing it underground and then to the shoreline. Plus, I mean, I don't know. Okay, so anyway, let's see if there's somewhere in between that would be a little less money. So what we need to do is we need to come up with an equation that describes this situation. So I have some unknowns. What I'm going to do is I'm going to call the distance from where I land to here, B to the refinery, I'm going to call that X, which will make this distance from A to B what? If I know the whole thing's 9 minus X. Do y'all agree with that? So then that would tell me wherever I am off A. All right, and so then I could get this blue line. This distance would be 4 squared plus 9 minus X squared. Do y'all agree with that? Yeah. Okay, so my cost function, I'd have 2 million times X, right? And I'd have 0.2 million times X and 0.3 million times whatever this length is. Does that make sense? All right. So my cost function is equal to 0.3 times the square root of 4 squared plus 9 minus X quantity squared plus 0.2X. Right? And what's my domain? Yeah. If X were 0, then it would be the 2.951, right? If X were 0, you would not have any over the land. And the most that it could be is if X were 9, right? And then you would be all over land, or you go straight from this thing to there. Okay, so our interval is from 0 to 9 for our X. Okay. All right, so let's clean this up a little bit. This will be fun. We need to find the derivative, C prime of X. All right. This constant out front just tags along, 0.3. You can think of this as 16 plus 9 minus X quantity squared to the 1/2 power. So that's going to be 1/2 times 16 plus 9 minus X squared to the 1/2 minus 1, which is negative 1/2, times the derivative of the inside. This is 0. And then it'll be, the 2 will come in front, 2 times 9 minus X, and then to the 2 minus 1, which is just 1, and then you have a negative 1. Y'all see that derivative? It's kind of tricky. It's a serious chain rule. And then plus 0.2.
Why do you not factor out, put the function aside? Why do you not
You don't want to take the square root of these two, do you?
Okay.
Because it's not allowed. You know, like if you do the square root of 4 plus 9, you can't think of that as 2 plus 3.
I was saying the 9 minus X, how come you can't take the square of 9 minus X while inside the...
Like FOIL it out?
Yeah.
Oh, you can, but I think it'll...
But if you did that, then you get a different derivative.
No, it'll be the same derivative. It'll just be harder to solve. You'll see in a minute. Probably. It's going to be tricky. I don't know. I mean, you could go ahead and do that. All right.
Wouldn't it be like, let's say you got the square root of 9, that'd be 81, and then plus 16, so that'd be 97 plus, that'd be the minus.
Yeah,
X
it'd be
squared.
18x squared and then plus x squared.
Get rid of that.
They're actually equivalent, though. They would be. It would be equivalent because here's your 18 minus 2. I mean, it would work out. It will.
Okay.
I promise it will, because that's just algebra.
Okay.
And so all we're doing there is the chain rule. But we may end up having to do that in a minute. All right, so these 2's are going to cancel. And so we will end up with, we have 0.3, we have negative 0.3 times 9 minus X and over a denominator of 16, or the square root of 16 plus 9 minus X quantity squared, and then plus that 0.2, and so I'm going to go ahead and get the common denominator, which will be the square root of 16 plus 9 minus x squared all over that. All right, and so remember, our derivative, we have to look at, this is going to equal 0 when the derivative equals 0. So this will equal 0, sorry, when the numerator equals 0. I took a Mucinex. Have y'all ever done that? I can't, it's like my entire brain has stopped working. I feel like none of the words that are coming out of my mouth are right. It's because my nose was so stuffed up, but it makes me. I think it might make me crazy. I don't know, but my lips are numb and I can't focus. I'm spelling numerator wrong. All right. Okay. So, and I don't know. 0.3 times 9 minus x plus 0.2 times the square root of 16 plus 9 minus x quantity squared. We got to set that equal to 0. So you might as well just start crying because this looks so hard, huh? I don't know. So I guess, I don't know, it might be interesting to have done it your way and multiplied it out first, but we're going to have to multiply it out now, which is not going to be very fun. We'll FOIL this out. We'll get negative 2.7, or distributive, plus 0.3x, and then if I move this over, it's going to be equal to, or, yeah, I'll do it. I'll move it over. Negative 0.2 square root 16 plus 9 minus x quantity squared. This is a real test of algebra. You guys might remember that what you want to do when you have a radical expression, the first thing you want to do is isolate it as much as possible, and then you square both sides. So now I can square both sides to isolate this radical. I'll get negative 2.7 plus 0.3x quantity squared is equal to this thing squared. Okay, and so then this thing squared, 2.7 squared, I'm just taking these from last year, 7.29. If you FOIL this and add them, collect them, it's going to be minus 1.62x. And then 0.3x quantity squared is going to be plus 0.09x squared. So that's just FOILing that out. And then this 0.2 squared is going to be yeah, I have a typo on my notes. Okay, 0.04, and then times this, which is 16 plus 9 minus x quantity squared. Okay, and then what you do is use the distributive property here and make it equal to 0 because this is going to be a quadratic. So we have 7.29 minus 1.62x plus 0.09x squared equals 0.04 times 16. Can you do this for me? Plus, all right, this is going to be 0.04 times, this is 81 minus 18x minus x squared. So we did end up having to do it, like you said. So 7.29 minus 1.62x plus 0.09x squared equals 0.64 plus, what's 0.04 times 81? 3.24 minus 0.04 times 18. 0.72x minus 0.04x squared. Okay, and then if we move this over, we're going to get 0.13x squared, right? If I move that one over, don't do that. So I'm going to move that one over to that. I move this 0.72x to live with this. All right, 1.62 minus 0.72 is how much? Well, I just need the difference. I know it's going to be negative. So 0.9, yeah. Do we agree? All right, and then this is 7.29, and it'll be take away these two. So take away 3.88. Anything?
3.41.
3.41? I'm so nervous because I guess I didn't finish this last year, and all my numbers are different. But I'm pretty sure that I did this wrong last year because when I had that 0.2 and I squared it, I didn't get 0.04. So was I losing my mind?
Maybe you're
I mean, 0.2 squared is 0.04. I know, but I'm on the Mucinex now, so I'm really nervous about my answer. And you guys were like, and the time's passed, and you don't really care. Half the time they just leak all the oil into the Gulf of Mexico, and so why are we doing this problem? Okay. All right. So x equals negative b plus or minus square root. Everybody pray for the... I'm just not feeling good about this, but okay. I think we can do it. I feel like y'all have been helping me. All right, so this is going to be 0.9 plus or minus the square root of 0.9 squared minus 4 times 0.13 times 3.41 all over 2 times 0.13. Is there more than one person there trying to get a number? See if you can't get that bad boy to work. If you have to leave, you're not going to hurt my feelings. This is the last. We're only like 3 minutes out, but I've already got you after class. Kind of slow start, too. Okay, so it's 0.9. Wait, let's see. 0.9 plus second square root 0.9 squared minus 4 times 0.13 times 3.41. Divided by 2 times 0.13. Please. Darn it. Yeah. No, we're in trouble. Where did I get the 0.9 from? I thought it was 0.09. Oh, no, that was...
Subtract 7.72 months ago.
All right. I'm going to have to look back at it. I'll look at it tonight and fix this. I'm sorry. There's a typo somewhere. It does work. I know that this answer works. I've done this problem before. I'm sorry. I'm out of it. I don't have it with me. Does anybody see it? No.
Well,
I love how this is recorded, too.